Hello, and welcome back to another week of Natural Science 150. My name is Brian Grimm, and today we will be talking about chemistry and beginning the scientific method step of hypothesis. Let's do it. All right, again, chemistry and hypothesis. In chemistry, we'll be talking about the role of chemistry in our lives. We'll be moving on to a brief history of chemistry and some important discoveries. Then we'll move on to the difference between hypothesis and theory, what makes a good hypothesis, and determining trusted sources. Let us begin with just the general what is chemistry. Okay, chemistry is the study of matter and its interactions with other matter and energy. Remember that matter interacts with other matter and energy. An example of that would be, greenhouse gases are on my mind from another class. So you've got energy in the form of light coming in from the sun. Remember, not all light is visible. Some of that UV light gets absorbed into the earth, for example, and it gets reflected back, not reflected, but it gets redirected back through our atmosphere in the form of infrared or longer wave, lower energy radiation energy. It comes out and it interacts with the matter in our air, right? The carbon dioxide, water vapor, not everything, but some of the things, and that energy affects the matter in the air, and it makes it move around and get warm. So it not only interacts with each other, but also energy. What do I mean by matter? It's anything that has mass and takes up space, right? If you have mass and you take up space, that's matter. It has physical and chemical properties. All right, physical properties include what it looks like, its color, its density, melting and boiling point, and then it also has chemical properties, right? So its ability to undergo a chemical change. Usually when we talk about matter, we talk about elements and compounds. Compounds of different substances, combinations of different substances are called mixtures. So an element is the smallest piece of a pure substance, right? It's characterized by a distinct number of protons in the nucleus, and it's given a space on the periodic table, identified by its atomic number. And then a compound would be a collection of elements, and then you'd mix them up into different substances called mixtures. I think that about covers it for this one. All right. Okay, let's look at the role of chemistry in our everyday lives. So here's 10 things that we're going to go over more in depth in the following slides. And I just wanted to say really quick, of course, this is not an in-depth be-all, end-all list. It's just a few areas that I thought we could look into and see what kind of role that chemistry plays in our everyday lives, right? So medicine and healthcare, food and nutrition, its environmental impact, a little bit about materials science, energy production, personal care products and cleaning products, textiles and clothing, home and construction, and finally we'll talk a little bit about technology and electronics. So for medicine and healthcare, we've got chemistry is fundamental to the development of pharmaceuticals, medical treatments, including drug formation and understanding how it's going to interact with your body, right? Safe levels, therapeutic levels for certain medications. And then biochemistry is where you'll learn a lot about just the chemistry of your body. To be honest with you, I long time ago started to go back to school and was taking a anatomy and physiology course, and I still remember it got to the point where it talked about muscle contractions and extensions, and it talked about sodium and potassium channels in the cells of your muscles, and how those sodium and potassium, which are elements, um, were able to open up and change the function of your muscle, or contracting and extending and everything like that. And I just kept wondering, well, how does that work? And got deeper and more interested in the how of those processes, which led me to a bachelor's degree in chemistry. So your body is an amazing chain of chemical reactions, and so of course you're going to need chemists, biochemists in the medicine and healthcare field, not only for understanding those chemical processes that run your body, but also for developing new drugs that help with various illnesses and diseases, and making sure that they are going to be safe in your body. So for food and nutrition, obviously chemistry is involved in food production. We've had breakthroughs in the last 100 years on food preservation, flavor enhancement for better or worse, nutrient analysis, food additives, again, for better or worse. And the study of biochemistry helps improve food quality and safety, which is definitely for the better, not much for the worse on that one. So it's chemistry has been fundamental in making food safer and more secure, and we're able to feed a lot more people and have a lot less food waste because of that. We'll talk a little bit about the environmental impact of chemistry, right? So it's critical in addressing environmental challenges, pollution control, waste management, sustainable energy solutions, right? And understanding the chemical reactions aids in developing strategies for environmental conservation. So as far as um, what I do, or have experience with in the past, as far as water distribution and municipal water distribution and wastewater management, I mean, chemistry plays a huge role in both of those things. On the wastewater treatment side, there's tons and tons of chemical reactions occurring all the time that's breaking down the organic waste that comes in to the treatment plant and creating a safe end product, whether that be water that goes back into the rivers that we all recreate in, or the solids that are separated out at the end of that process that go into composting. So a huge, huge environmental impact that chemistry plays a role in. For material science, right, it's central to the design and development of materials with specific properties. Um, does it conduct electricity? Is it magnetic? How is its does it bend or does it break? What is this material's tensile strength? Right, we get things like carbon fiber out of this, plastics. So innovations in material science impact the creation of new technologies, from clothing to electronics. Moving right along to energy production. Chemistry is involved in the study of energy storage, conversion, and efficiency. Research into chemical processes contributes to the advancements in renewable energy sources and fuel technologies. Chemistry, we're talking about like refinement of oils, right? You pull crude oil out of the ground. It's not, you can't just pull it right from the ground and put it in your vehicle. It needs to be refined. Chemistry and chemical engineering plays a giant role in processing, storing, refining chemicals for gasoline. For a long time, lead was an additive in gasoline, until we found out, which chemists were a large part of this, found out that having lead in the gasoline um, led to having lead in the air, and people breathing that in from combustion from these gas engines. And you probably have it as common sense now, but breathing in lead is not necessarily a good thing for the health of your population. So that got removed from gasoline that's no longer in our gasoline, and chemists had a large role in that. For personal care products, it's integral to the formulation of cosmetics, skincare products, and toiletries. Understanding chemical properties helps in creating safe and effective personal care items. These are going to be, you're rubbing this stuff all over your body, in and out, right? If you think about toothpastes and mouthwashes. And so we want to make sure that these items are safe, and chemists play a large role in that as well. For cleaning products, a lot like personal care products. I mean, we spray these things all over our house. We clean our dishes with them and then eat off of our dishes. We wash our clothes, right? Cleaning products. It's the development of cleaning products and detergents. Um, we need to have knowledge of chemical reactions that facilitate the creation of products that not only remove dirt and contaminants, but are also safe to use around your family and your pets. Um, and then textiles and clothing. Chemistry is essential in the dyeing, finishing, and production of textiles, understanding the properties of fibers and fabrics, and which contributes to the creation of durable and comfortable clothing. So wide range of um, ways that chemistry is involved in your everyday life, and some of them in a way that you don't even really think about on a day-to-day basis. Okay, and the last couple we're going to talk about as far as how chemistry is involved in your everyday life is home and construction and technology and electronics. Chemistry is involved in the development of building materials, paints, adhesives, and innovations in construction materials contribute to safer and more durable structures, right? So I know a lot of times that this is spread out through engineers and chemists. In fact, when I was doing my engineering degree, I, with a chemistry background, often helped other engineers look at, especially in the testing of some of their items and how they held up to the um, exposure of different chemicals and what happened when they were exposed to different chemicals and how to measure that. So highly integrated with other scientific fields, but definitely a large part of the home and construction industry. And then last, again, is technology and electronics, right? It's crucial to the production of semiconductors, batteries. I mean, chemistry is how batteries work. So having a general idea of the chemistry behind batteries can help you improve in that technology, as well as knowing about other electronic components. And advancements in chemical processes drive innovations in the electronics industry. All right, so that was a brief look at how chemistry plays a role in your everyday life. And now we'll go right into just a brief history on chemistry, an unfortunately brief history on chemistry, but I want you all to be able to stick with me at least for a while. I highly recommend anybody that we talk about or any idea that we talk about to go if you find it at all interesting and learn more about it, because there's a ton of interesting stuff in the world of chemistry. Before we get into chemistry, let's talk about its precursor, which was ancient alchemy. I'm sure you've heard alchemy before, heard of alchemists before. And what are they all about? What is that all about? Okay, and what it is, it's a proto-scientific tradition before modern science, and it existed before and during medieval times, long time ago. And it held a wide range of beliefs, practices, and experiments. Some sources, when they talk about alchemy, say that it had two goals, and this is a drastic oversimplification, but one that I quite enjoy. But alchemists, essentially, when you get right down to it, they wanted to get rich and live forever. And how 100% accurate that is, I don't know, but I think it's pretty good um, basic idea. And where that comes from, the get rich and live forever, is a lot through ideas like the philosopher's stone, right? There was thought to be some way to, they call it transmute or transform base metals like lead, tin. I don't even know if tin was a thing then, aluminum, silver, into gold, right? Take something and turn it into gold. Another example of the get rich and live forever theme would be the elixir of life. They believed that there was some way, something that you could drink or eat or take into your body that would grant you eternal youth or immortality, right? And this quest of longevity was intertwined with the pursuit of spiritual enlightenment, right? Um, not only would you live forever, but you would be somehow an enlightened being. Um, Ancient alchemy, right? When we talk about the modern scientific method and that last step that we talk about, which is share results, and as you've mentioned in quizzes or online discussions or whatever it was, um, sharing results is an essential step to the scientific method, right? It kind of puts our money where our mouth is. It says, "Hey, look, this is what I saw. This is what I did. These are the answers I got. This is my conclusion. Let's further the knowledge, or let's see, maybe somebody sees something that I did wrong or could have done better." And we really want to make a culture around sharing that information and furthering and advancing our pursuits and holding ourselves accountable. And I think that alchemy, they were a little bit more, a lot of the people that were alchemists were a little bit more self-centered, I suppose is one way you could put it. They wanted to make money and profit off of what they were learning. So a lot of ancient alchemical texts are rife with symbolism and allegory, right? So the texts and symbols were filled with symbolic language. It was coded. There was a lot of secret knowledge that was kind of passed from one person to another. And again, a lot of it was because they were able to make money and a living doing that. And they weren't big into sharing their findings unless it could benefit them in some way. Now, alchemy did give us some good things. Alchemists engaged in experimental practices. They got really good at distilling, sublimating, and purification of various substances. Right? It was they were trying to turn things into golds. You're really trying to separate out various mixtures and compounds and really isolate pure substances. And so there was a lot of advancements in that way. Um, there was a really big tie-in for spiritual and material goals. The transformation of materials in the laboratory was interconnected with spiritual transformation and enlightenment. So it was really a little bit secretive, a little bit more tied to spiritual and religious ideas, and but it did again have some really good advancements for science in general. And it had a wide geographical spread. Right, it may have started in or around ancient Egypt, but it traveled all over throughout Greece, Islamic civilizations, medieval Europe, and China, and different regions all contributed in various ways to the development and evolution of alchemical theory and practices, as well as science in general as a whole. As science progresses forward over the first 1,000+ years of the modern era, we start to transition out of alchemy and more to what we would think of as a modern science. Less mystical and speculative aspects to more empirical approaches. This was a gradual process that occurred over several centuries. And there were several key factors that contributed to this transition. The rise of experimentalism, which was characterized by systematic and controlled experimentation. And we talked about some of this in one of our first lectures about some of the people who were saying, hey, we need to run these experiments, and this is exactly how I did them. And again, they begin to share those ideas. And it became a characteristic of modern science. The other thing that occurred in the like 1500s on, 1600s on, was a standardization of nomenclature and chemical education, right? So more schools, the importance of standardizing nomenclature. What I mean by nomenclature too is giving chemicals and chemical compounds specific names so that no matter where you were, you could know what someone was talking about. I mean, if we all called oxygen different things, it would be much harder to share our ideas and have everyone be on the same page, right? So it eliminated mystical and obscure language often associated with alchemy. The influence of the scientific method. Alchemists' reliance on mystical and symbolic language started to give way to more rigorous and standardized scientific language and a method of doing science, which we, of course, have been talking about. But there were also some advancements in instrumentation, microscopes, good balances, and microscopes. Telescopes is the other one, and it allowed for more accurate measurements and observations. And then, of course, communication and publication. There was a much more collaborative aspect of science, and it encouraged the development of a collective evidence-based approach that, again, we would share with others just to develop the knowledge that we were gaining as scientists throughout the world. Okay, now we've made it to the 16th to late 18th century. We've made it through alchemy and the transition, and now we are in the full-blown scientific revolution. This was a shift towards evidence-based science, laying the foundation for scientific rigor and methodology that characterize modern chemistry and science as a whole. Okay, we talked about some of these in the last slide, but a shift to empirical methods, a move away from deductive reasoning. I think this, therefore this, and relying on the authority of ancient texts. Well, this guy, it's always been known to be like this, so that's the way it is. And there was an increased emphasis on observation, experimentation, and the scientific method. Not just believing what people said, whether that was through thought experiments or logic, but actual tests, right? Not just saying, hey, this is the way it's always been thought of, and this is what we've agreed on, but saying, okay, well, if that's what's agreed on, let's see it in action, right? We want to see it in action. Many scientists helped create this idea of a scientific method, this systematic approach to empirical investigation. We want to make observations, form hypotheses, do experiments, analyze the results with mathematics and statistics, and of course share that data with others. There was a huge leap forward in mathematics and using mathematics to explain natural phenomena, right? And create laws which were able to make predictions about this natural phenomena. We got away from the Earth being the center of the solar system. We have better telescopes. Galileo, mathematicians like Copernicus and Newton were looking at planetary motion, and they all worked together, and we had huge advancements in astronomy. Galileo and Newton and everyone else came together, and we had just have what is now modern physics, which we use still today. And the scientific revolution also had a very big impact on society and culture. It changed established religious and philosophical beliefs and made it more accessible to the general public. Okay, now I want to talk a little bit about chemical nomenclature, atomic theory, and the periodic table. Okay, before the establishment of a standardized nomenclature, which again is just a naming system, chemical compounds are often referred to using descriptive terms, right, which led to confusion and hindered clear communication among scientists. We needed a way to all know what we were talking about when I say nitric acid, right, versus nitrous oxide, right? All these things have names, specific ways of naming things that are known, not just in one country, but there's an international system of naming these compounds, and it helps with collaboration, expansion of knowledge, and advancement of chemical theory. And then it helps, of course, support chemical education and growth. Okay. Moving on, in 1800s, early 1800s, John Dalton came up with the idea of atomic theory. It involves the following postulates, right? Elements consist of an indivisible small particle, which we know of as an atom. All atoms of the same element are identical. Okay. Now we know that all atoms of the same element have the same amount of protons in their nucleus. Okay, that's what tells them how they're named. Or that's what gives them a spot on the periodic table, and not tells them how they're named, but tells us how they will act in a certain way. Atoms can neither be created nor destroyed. Well, we found out that if you split an atom, it destroys a lot more than the atom. And then the compounds are formed when atoms of different elements join in simple ratios to form molecules. So this was a really important theory. He also proposed symbols for atoms of different elements. This was later replaced by different notation using letters instead of symbols. But this was getting away from like alchemy and everything else before that, where they had there was 4 elements: water, earth, fire, and wind. And now we know that there are so many more elements than that. And then came the periodic table. So there was a Russian chemist, Dmitry Mendeleev, who unveiled his groundbreaking creation in 1869. And he arranged the atoms based on their atomic masses and properties. He even knew to leave some spaces in the periodic table for undiscovered elements. And it not only provided a systematic way of organizing the elements, but also revealed that the way the elements are set up in the periodic table tells you something about how the elements behave. Whether you've got a spot on the periodic table for metals and nonmetals and noble gases, which don't easily interact with other elements. So it was really quite remarkable that we were able to organize these in this way. Not only that, but the amount of protons that they had and really affected the way that these elements interact with each other. Okay, so let's look at some of the 20th century advancements. We've come all the way back from alchemy through the scientific revolution, and now we'll look at, and then early 1800s, now we'll look at the 20th century advancements. So right at the turn of the century, the discovery of the electron, right? So of course you've got a nucleus in every element that has a protons and neutrons, positively and neutral charged, and they're surrounded by a cloud of electrons, or negatively charged parts of your atom. In the 1900s, we had quantum theory, the development of spectroscopy, which was let us have a better understanding of chemical compounds and how they interact with light and energy, and a way to separate them. In 1928, the discovery of penicillin. Then we had polymer chemistry, that's plastics and rubbers and things like that. And then in the 1930s also we had development of chromatography, another way of separating chemical compounds and mixtures based on their properties. In the late 50s, or in the 50s, we had found the structure of DNA, the building blocks of life. And then in the 90s, we had a big push towards green chemistry and environmental chemistry. All right, moving right along, we'll start our next step of the scientific method, which is, of course, hypothesis. So we'll talk about how we use the word hypothesis and how it's closely related to, but different from another word that gets thrown around quite a bit, which is theory, right? And these are a couple of quotes from a book called A Beginner's Guide to the Scientific Method by Stephen Carey, and he talks about the word hypothesis, right? In just general language, it can mean anything from a vague hunch to a finely detailed conjecture. In general, however, the point of characterizing a claim as a hypothesis is to note that there is something tentative and unproven about that claim, right? So maybe people don't generally walk around saying, "Oh, I got a hypothesis," right? But it's not just a vague hunch, right, or a finely detailed conjecture. It's used to say, "Hey, I have a hypothesis, and in fact, my hypothesis involves a kind of an if-then statement, right? My hypothesis is that if this happens, then that happens." And honestly, there's a lot of background that goes into even making a hypothesis, right? Generally, you don't just say, "Hey, if I do this, then that's going to happen." It's based on my previous experiences or based off of what I know about this topic. If I do this, then that will happen, right? There is something tentative and unproven about that claim, but it is also based on kind of what we know. Maybe it's even based off of a theory, right? So this word gets used a little bit more than hypothesis, kind of outside the way we like to think about it, especially when doing science, right? So theory does not always imply the kind of tentativeness associated with hypothesis, right? You may have a hypothesis about something that we don't really know about 100%, or maybe it's a new way of doing something that we understand, but there's something that you're trying to prove. Theory does not have that. It's a well-developed, well-confirmed body of explanatory material, right? The theory of gravity, the Big Bang theory, the theory of evolution, or the germ theory of disease. We all know if you don't wash your hands, especially if you're a doctor, you're going to get people sick because there are germs and we need to wash our hands to get rid of these germs. That was not always known. But when you say theory, it doesn't mean I have a theory, it may or may not work. No, it's, hey, I have this theory that this is going to work because we have seen it work time and time and time and time again, and hundreds, if not thousands of people have proven this theory to be correct, right? So there's that idea right there. Again, when I talk about a good, and I'm putting air quotes in even though you can't see me, hypothesis, good may not be the best word from this. I don't really like ideas of being good or bad, or a hypothesis as being good or bad. But there are ways that we can make sure that we're making a very useful and straightforward hypothesis, a hypothesis that we can move forward with. Right? First off, we want to state it in the correct terminology. Right? We want to know what we're talking about and not leave anything up to the imagination. Right? We want it to be brief and as clear as possible. We want to state an expected relationship or difference between two or more variables. If we adjust this, then we will see this outcome. We want to actually be able to test our hypothesis. It's not useful to have a hypothesis that you can't figure out. And we want it to be grounded in past knowledge gained from a literature review or from a theory. So now I'm going to give you an example of an unacceptable hypothesis, right? Um, So we're comparing a couple of age groups here, and we'll say, hey, you know what? The older age group is more likely than the younger group to do press-ups and eat porridge first thing in the morning. This was not obviously mine because I probably would have called them push-ups and oatmeal, but we'll move forward. What's wrong with this hypothesis, right? The older age group is much more likely than the younger group to do press-ups and eat porridge first thing in the morning. First off, it's not very clear. What age groups specifically, right? Are we talking 15 to 20, right? Are we talking 15 to 25, 25 to 45, 45 to 60? Which age groups are you talking about? And also, what do press-ups and porridge have to do with each other? Maybe an older age group is more likely to eat, I'm going to quit calling it porridge, oatmeal, right? That's a good one. And obviously, a younger age group is more likely to do push-ups in the morning. It's just not a very good hypothesis, right? First thing I want to mention, even though I've said about 6 other things so far, is a hypothesis should never be double-barreled, right? Why are we looking at sit-ups and oatmeal in this, or push-ups and oatmeal in the same hypothesis? Let's narrow it down a little bit. There's probably going to be different results for the separate variables concerning push-ups and oatmeal. They need to be separated, right? And secondly, there's no clear stated relationship between the variables. There's no if-then type statements. There's nothing there suggesting how we would test this hypothesis. So this is what I mean by just a not very good, useful, testable, being able to move forward with hypothesis. Okay, the last thing that we are going to look at for the first part of the week 5, 6 lectures here is how to determine a credible source. So I've got 3 different possibilities of, there's many more, but for our class, 3 different possibilities of ways of determining whether a source is credible, right? So we're going to start with the 5 W's. Who is the author? What is the purpose of the content? Where is the content from? I listed that twice and now I see that. Okay. Why does the source exist? And how does this source compare to others? So there's 5, trust me, there. Okay. And all of these kind of have the same idea, right? Who's the author? What's their background? What's their purpose for publishing this? Is it to get attention and maybe bolster some public platform? Or is it just they want to know? Where's the content from? Who's publishing this? Is it a reputable scientific or otherwise or news journal or conglomerate? Why does the source exist? So again, purpose. Is it objective? Are they doing this to further knowledge or to report on something important? And then how does this compare to others? If you look up 10 different papers on this subject, are they all kind of agreeing with each other? Are they using each other as references and looking at each other's work and trying the experiments again and coming up with similar results? Or if you look up 10 of them, is this first one that you found completely different than the other 9, right? And in that case, why, first off, and secondly, is there a reason whether questions 1, 2, 3, 4, and 5, is there a reason that this person is getting a different result from one of the things we talked about beforehand? So pick one that you like. There's the 5 W's. There's the SMART check, right? These are acronyms now. SMART. Who's the source? What's their motive? Who wrote the story? Review. Is there anything included that jumps out as potentially untrue? And the 2 source test. How does it compare to another source? So that's SMART. The other one is the CRAP test. 2 A's in that one. Uh, Currency. What's the timeliness of the information? What is this post or article or paper getting them in return, right? Is it just, again, is it just for furthering knowledge, conveying something important? So that's currency. Relevant. How important is this information for what you are trying to accomplish, right? Authority. Who is the source of the information? The accuracy, truthfulness, or correctness of the information, and the purpose. Why does it exist? So CRAAP. We'll probably do something where I have you look at the 5Ws, the SMART check, or the CRAP test, or at least have you reference it and say, hey, does it pass all these check marks, right? So, and just when you're looking at and everything, this could be social media posts, it could be watching the news at night, it could be um, actually doing research for our final paper when we have that due later this year, or your summaries from scientific articles. So just keep these in mind, and we will definitely come back to them in the future. All right, that is it for part one of weeks 5 and 6. I didn't post this last week. I'm posting it this week along with a second lecture for this week. Ultimately, I do believe it'll be a light week. Just listening to these lectures. There will probably be a discussion post next week. Well, I think we got a quiz next week. But we'll definitely have a little bit more interactions with these lectures. I think this week is only a reading assignment and a scientific literature review. So definitely watch this one. You have already. Watch the next lecture, and I'll watch for your assignments to be posted on. And have a good week. Thank you.